Good morning, dear student. In today's lecture, we are very much interested in the important component or important points regarding to the superconducting material is the types of superconductor. So, the classification is based on the behavior of superconducting material in external magnetic field. So, we can say that depending on the behavior of superconducting material in external magnetic field, they are classified into two categories. So depending depending on the behavior of superconductor depending on the behavior of superconductor in external magnetic field in external magnetic field external magnetic field, they are classified into two types. External magnetic field, they are classified classified into two categories into two categories into two categories. One one that is your type first superconductor, type first superconductor or it is also known as soft superconductor. Soft superconductor. One that is type first superconductor, and the second that is type second superconductor. Type second superconductor. So depending on their behavior in external magnetic field, they are classified into two types, that is type first superconductor, which is also known as soft superconductor, and type second superconductor, it is also known as hard superconductor. hard superconductor Hard superconductor. So let us discuss one by one the type first and type second superconductor. So let us discuss the first one, that is type first superconductor. Type first superconductor. So for these two types of superconductor, that is type first and type second, or soft superconductor and hard superconductor, we should plot a graph of applied magnetic field, that is the strength of the applied magnetic field versus the intensity of magnetization. So the graph is same, that is along x-axis and along y-axis. The components are same, but the behavior of the graph is different for soft superconductor and for hard superconductor. So this is your soft superconductor. Soft. And we plot a graph of applied magnetic field. Applied magnetic field, that is H vector versus the intensity of magnetization. The intensity of magnetization, how much the material get magnetized, the intensity of magnetization along this y-axis. So we know that as the magnetic field strength is increases, the intensity of magnetization is also increases. Okay, so as the magnetic field strength is increases, the intensity of magnetization is increases. So we get such a kind of graph. We get such a kind of graph up to a point, and after that, up to a point, that is up to HC, capital HC. HC, it is denoted by critical magnetic field. So when the applied magnetic field or the value of H vector, it is goes up to this HC, that is a critical magnetic field value, then the superconducting material, it will convert into normal state. That is, the superconducting state of the material, it is converted into normal state. That is, superconducting material, it is converted into normal conduct. So this is the graph for type 4 superconductor. As the strength of magnetic field is increases, so as the strength of the magnetic field is increases, the intensity of magnetization is also increases. It is true up to this critical value. So we already discussed the critical temperature, below which the material acts as a superconductor and above which the material acts as a normal conductor. Same is the case here. This is the critical magnetic field. So below which the material, it is act as a superconductor, and above this critical field, the material, it is in normal state. That is, it is act as a normal conductor. So this region, whatever the region, this region in which the material is in superconductor state, and we already know that the superconducting material follows the Meissner effect. So up to this point, whatever the area is there, it is the material, it is in superconducting state. That is, it will follows Meissner effect properly. So above this critical point, above this critical magnetic field, the material, it is sharply converted into normal conductor. So the resistivity is also increases. So up to this, it is in superconductor state, so the resistivity of the material is 0. But from this critical magnetic field, so whatever the value of this critical magnetic field, above which the material having a certain resistivity, and it is act as a normal conductor. So so this is the area. From here, it is act as a normal conductor. So this is the graph for type 4 superconductor. It is a soft superconductor, means very small amount of magnetic field strength is required to convert the superconducting material into normal conductor. So if you see the graphical representation for type 4 superconductor, again, the important point is that these type 4 superconductors, they are perfectly diamagnetic. They are perfectly, if you see the properties, they are perfectly diamagnetic. Means below the critical field, they are in superconducting state, and they are perfectly diamagnetic. We already discussed that the superconducting material behave as a diamagnetic material, and therefore they are perfectly diamagnetic below the critical field. Okay, because it is in superconducting state. Again, the second one is that whenever it is in superconducting state, it will follows the Meissner effect strictly. The second important point is that they follows Meissner effect strictly. They follow Meissner effect strictly. That is, up to critical field strength, it is in superconducting state, so they will follows the Meissner effect. We already discussed the Meissner effect in previous lecture. And above the critical magnetic field value, they does not shows Meissner effect, so they follows Meissner effect strictly above critical field, below critical field, and above critical field, they do not shows the Meissner effect. They are perfectly diamagnetic below critical field. Again, the value of critical magnetic field is very low, that is up to 0.1 Tesla. So whatever the value, to convert the superconducting state into normal conductor, so we required the magnetic field strength, it is up to 0.1 torr. So the value is very small, the value of critical magnetic field is very small, and therefore the superconductor find very limited application because of their low critical magnetic field. So they having very limited application, because of their lower critical magnetic field. So this regarding the type first superconductor. So in this lecture we discuss the types of superconductor. That is, depending on the behavior of superconductor in external magnetic field, they are classified into two categories: type first and type second superconductor. Type first, it is also known as soft superconductor. Type second, it is also called as a hard superconductor. So we already discussed the type first superconductor. Let us discuss the type second superconductor. Type second superconductor. Type second superconductor, it is also known as hard superconductor. Hard superconductor. And if you see the graphical representation for this, again the parameters are same along x and y axis, that is the m vector and h vector, that is strength of applied magnetic field and the if magnetize the percentage of magnetization. Okay, so the magnetization, how much they get magnetized. So for type second superconductor we get such a kind of graph is there. So in this case, if you see the difference between this type first and type second, so here so this is the region. So this is up to this is the first region, and from this is your second region. So this is hc1 critical magnetic field 1, and this is hc2 critical magnetic field 2. So you should remember the behavior of this superconducting material, that is type first and type second curve for the effect of magnetic field versus the magnetization. So we can't get the same graphical representation for hard superconductor. So in this case, if we see, there is a two critical magnetic field value, hc1 and hc2. So again it is the magnetization, we already know that as the critical magnetic field is increases, the magnetization is also increases. But at hc1 the material it is in superconducting state, it is not directly converted into normal conducting state. So we required much higher critical magnetic field, that is we increases the critical magnetic field, we increases the magnetic field value up to hc2, that is critical magnetic field second. So up to this point the material, it is not perfectly conductor. So above hc2 the material, it is a normal conductor. But from hc1 to hc2, whatever the region is there, okay, but, we already discussed, that is type first and type second. So we divide this portion into two parts, first and second. So this is a superconducting state, whatever the region, it is your perfectly superconducting state. But this region, it is not a pure conductor, It is a mixture of conductors and superconductors, because we required external magnetic field to reach Hc2 to convert this superconducting material into normal conducting material. So uh, the first part, it indicate it is a perfect superconductor, and the second part, it is a mix superconductor. It is a mix superconductor. So you should see the difference. The first part, it is your perfect superconductor, and second is your mix superconductor. So to convert this mix superconductor into normal conductor, we required very much high magnetic field value, or we reach up to Hc2, that is critical magnetic field second. And the third one, so from this is your third part, and it is your normal conductor, normal state. This is your normal state. So first, that is perfect superconductor, second, that is mixed superconductor, and the third, it is your normal state or normal conducting state. So if you see the characteristics of this type second superconductor, they does not follow Meissner effect strictly. They do not jump to normal state. They shows perfect diamagnetism for field less than Hc1. So we already know that they do not follow Meissner effect strictly. That is, as the critical magnetic field reaches to Hc1, it is not convert into normal state. It will shows some mixed character of superconductors and conductor, and therefore they does not follow Meissner effect strictly. Don't follow Meissner effect. Don't follow Meissner effect. Again, the second point is that they are perfectly diamagnetic for field less than Hc1. Perfectly diamagnetic for field less than Hc1. So above Hc1, it is not perfectly diamagnetic. Okay, they are perfectly diamagnetic for field less than Hc1, since the large magnetic field is required to destroy the superconductivity. They are considered as a hard superconductor. So we already discussed for type first superconductor, we required very less magnetic field, external magnetic field, to convert the superconducting state into normal state. But in this case, for type second superconductor, we required very much high or large magnetic field to destroy the superconductivity properties, to destroy the superconducting state, and therefore this material is called as a hard superconductor. And because of this property, that is, we required high large magnetic field, they are having many practical applications. So the two important point is there, that is, they don't follow the Meissner effect. They are perfectly diamagnetic below less than Hc1. Again, the third important point is that we required very much large magnetic field to destroy the superconducting state and convert the material into normal state, and therefore this type second superconductor, it is also known as hard superconductor. And due to this property, they having many practical applications. So this is all about the type first and type second superconductor. In next lecture, we will discuss some important properties of superconductor and the remaining points of this chapter. Thank you.